Hello, my name is Flavius Penescu, and this is Physics 2, Lab 5, Magnetic Braking. This is the table of contents for the lab, and the purpose of this lab is to give students a better understanding of magnetic fields, bar magnets, and Faraday's law. The experiment observes the interaction of a bar magnet with the magnetic field of the Earth. We will use the formulas we were taught in class to calculate values such as magnetic field and magnetic force. Here are the fundamental physical principles. We have the magnetic field of a bar magnet, magnetic flux and its derivative with respect to time, Ohm's law, Faraday's law, magnetic force on a falling magnet caused by a loop, Lenz's law, and momentum principle. Here are relevant formula. As you can see, we have Lenz's law, Ohm's law, and the magnetic field and magnetic force law. Here's a diagram of the setup and the values of the setup. We have a tube length of 0.32 meters, a width of aluminum foil of 0.006 meters, an inner radius of 0.02 meters, an outer radius of 0.026 meters. The magnet weighs 0.024 kilograms. The magnetic dipole moment is 3.206 newton meters per T. The average time taken to fall through the tube is 1.26 seconds, and the time taken per the computational model is 1.32 seconds. Here's the computational model, and here are the checkpoint questions. Why can't we use a ferrous tube? A ferrous tube would cause interference with the magnet because it would contain iron, which runs the risk of becoming an induced magnet. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? The magnet falls slower due to the tube than it would in free space. Here are the results from the computational model. As you can see, the plot shows velocity versus time. The velocity starts out real fast until the tube starts slowing down the magnet, and then it has a constant speed until it hits the bottom. The actual time in the tube was 1.26 seconds, but the time in tube due to the computational model was 1.32 seconds. Supplemental questions part A. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? Clockwise would be red and counterclockwise would be blue. What happens to the dynamics of the system if you flip the magnet around? This would mean that clockwise would become blue and counterclockwise would become red. How does the total time in tube of your real-world system compare to that of your computational model? How might the computational model be made more accurate? The computational model took a little longer, and this is most likely due to other factors such as air resistance and friction. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? There are two forces acting on the bar magnet, magnetic force and gravitational force. Supplemental questions part B. What if the resistivity of a conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? The magnet would not fall through the tube because the braking force would be equal to the gravitational force. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would disrupt the normal flow of current through the rings of currents in the tube. What would likely happen is the braking force would be weaker because there's less current flowing. In conclusion, we discovered the effects that a current loop would have on a bar magnet. Thank you.